Because there's a final.
Yeah, the final doesn't get dropped. I don't know.
It's slow enough that there's, yeah, it's slow enough that it's for the final. And classes per week, so there's 8 classes on the final. Yeah. After this class, will be 8 classes.
I'm like, I'm dude, it's stuff over T, DOT. It's the easiest integral second to like a power function. It's like, you should know how to take this integral.
I got the thing to control the power function only part. Nothing else. I'm wondering where is my
I think. Well, I think you need 100 and one of the. I actually think you need 200, which is funny because it's really like there's only some partials a little bit, not so very like, but it's not like most.
Self-city pretty quick. You know,
That's the reason. So are you way too because when I was like, yeah, we're gonna do all of integration.
And then for sometimes
Integration. Oh, very, like, it's not hard. It's stop, more stuff, like, it's not that hard. Multivariable calculus is not that hard.
To be fair, we do mostly like super easy derivatives. Like,
yeah, you could make the derivatives calm. And even then, it's like.
yeah, these are overcomplicated.
And it's not that derivatives. Like the hardest derivative I think I still remember doing was actually the one for, it actually he showed us in last year's in physics 121. Where he was like, I'm not actually gonna make you guys solve this, and then he did that in math 101, and it was like, oh, it's actually really not that bad. You have to simplify a few things, it's also a constant solid, but it's really not that bad.
My favorite is deriving the black body.
It's so disgusting. That's like the first time. Have you ever derived formula?
With like three guys, yes.
No, like derived it by completing the square.
There's, I've seen that one, I haven't done it, but I've done.
It's not that hard, but it's kind of annoying. But like the first time you do it, it's like, oh my god, there's so many letters, and then by the end, it's like, oh,
Look at these guys, nerds. Imagine knowing math. Could not be me.
yeah. I did that for one of the math questions. I was like, you were supposed to find the closest distance, the closest distance between two points. I'm like, I don't actually know how to do this. Instead, what I knew it was really dumb. I instead used the Pythagoras.
That's actually how you do it.
Oh, that's actually how you're supposed to do it.
Yeah.
You're supposed to use Pythagoras and then complete the square to get your smallest p value.
Yeah.
Dumb.
Yeah.
Did they teach us that?
Yeah. You went over it on like the first day.
I was
And then that was on the test.
well, I didn't do anything
No, but literally for this assignment. For math,
yeah.
there's a question. What's the closest?
no.
distance?
Oh, yeah.
This point, this function, what's the point closest to this?
Well, no, thank you.
That's just a constrained optimization.
Oh, it is?
Yeah.
Oh, I didn't know for it.
It's like, that's just putting constrained optimization into like different.
I ended up just having it be. I used my Pythagoras and the distance calculation. And it's literally the square. Which has worked, but I was like, this is dumb. There's no way, there's no way you didn't do them all.
Yeah, I was like, maybe 30 signals per pole, all filled with these and so like eventually I did like
I don't know, I just like, here's a sign.
everything over
That's like,
Yeah, also they want seven.
They're not worth.
And then modulates, maybe not five.
You can save those entirely.
Why not three or?
You literally, I don't know.
Rate wise, you wouldn't suffer that much, but I don't think I would let my own
Actually, to do is math is matrix.
especially for the work one.
Oh, yeah, that's something.
Okay, so let's get started. What we're gonna talk about today are diodes and then a very common application of diodes. So and some of what we talk about today will be relevant to the lab that you do tomorrow. So we're gonna try to design this so-called rectifier circuit, and the idea is, can we take a sinusoidal or AC voltage and convert it into a constant voltage, a DC voltage? And this is an important application because what the power that's delivered to our homes are sinusoidal signals, but all of the devices we use, phones and tablets and laptops and all that stuff runs on batteries that supply a constant voltage. So what we need to be able to do is to take the AC voltage available from the outlets, convert it to DC so that we can charge the batteries that run all of our devices. So the diode is going to be a key component to this, and what a diode is it's like a one-way valve. It passes current in one direction, but not the other. And so what we'll start with by kind of writing down a fluid type analogy for the diode. So the diode is a semiconductor device that acts as a one-way valve. And what I mean by that is it passes current in one direction, but not the other. Next week, we'll actually talk about some basic stuff about semiconductor materials, and we'll see how to construct a diode, like how do you actually design and build a diode. We'll do that next week. For today, let's just understand what a diode does and how it can be used. Okay, so let's do like a fluid analogy. So what we're gonna imagine is we've got some kind of pipe, and we're going to try to flow fluid through that pipe. So the pipe has some kind of wall thickness, like so. Okay, so to flow fluid through a pipe, we need to establish a pressure difference across the pipe. So in electronics, if I want to initiate a flow of current or a flow of charge, what I need to do is I need to establish a voltage difference across my wire. For fluids, if I want a mass flow of water or something like that, I need to put, say, a higher pressure on one end than the other end to get the flow to go in a certain direction. So we need to establish a pressure difference across the pipe. Okay, so we would have, say, P2 here greater than P1, and we'll put P1 over here. And if we do that, then we can get a flow of fluid. So maybe these are like our fluid particles or something. There's a lot of them. I'm only drawing a few representative ones. Okay, so pressure differences drive the flow of fluid. So how are we going to make our diode in the fluid analogy? I'm going to start with the same sort of pipe. So I can do better than that. So we'll draw our pipe here. And I'm just going to add one little feature to our pipe. So there's the wall thickness. I'm going to make the wall have a little step at one point, like so. And we'll put a similar step over here. So, all right. And what we're going to do is we're going to put a little flap in here. And so my flap is going to be on like a little hinge. And this flap can be, well, I'll put it pointing down for now. This is like a little gate. So what happens here is if we're flowing fluid from left to right, it will push the gate open and we'll have our water current running. If, on the other hand, I flow my fluid from right to left, so I have the right side at high pressure, then that flap, the gate can't open and there's no flow of fluid. So we'll say if this, what did we call this? We call this side P2 and this is P1. And we could say if P2 is greater than P1, we get fluid flow from left to right. And the gate is pushed open with a non-zero current. If, on the other hand, P1 is greater than P2, the fluid tries to flow from right to left, but it gets blocked by gate. So this is a one-way valve. One-way valve. All right. Let's think just a little more subtle than that. It's if the pressure difference P2 is greater than P1, so we have the water flowing in the right direction. Let's imagine the case where P2 is just slightly higher than P1. So that pressure difference is there, but it's tiny. In that case, the gate has a certain amount of weight. In fact, what it really has is a moment of inertia, a resistance to being rotated. And we need to apply sufficient torque on the gate to cause it to open. So we have to overcome a barrier, an energy barrier to open the gate. So if P2 is greater than P1, but by just a tiny amount, then we don't apply sufficient torque to open the gate. And the fluid current will be zero. So we need to at least provide a big enough pressure difference that the torque applied to this gate is sufficient to open it up. Really, what we have to do is we have to do work on this gate. There's a certain amount of energy we have to apply to open it and then let that fluid flow. So we have to overcome a, I don't know, energy barrier to open the gates and initiate the flow of fluid. So if I was to try to plot something like, let's say delta P is P2 minus P1. So that's going to be on my vertical axis. Like so. And then, actually, no, I'm going to put delta P on my horizontal axis. I'm sorry. So delta P is P2 minus P1. And then fluid flow rate, or equivalently, the fluid current will be on my vertical axis. So let's think about what that would look like. If this delta P is negative, then the pressure difference is applied in the wrong way. The gate is just jammed up against that little step in the pipe wall. And so in that case, the fluid flow is 0. Okay, so that's clear. We get no current when the pressure difference is the wrong sign. And then if I make this delta P just a little bit positive, it still doesn't have enough energy, doesn't have apply enough torque to our gate to open it, and we have 0 current. But eventually, once that pressure difference gets sufficient, then we reach a point where the gate is pushed open, and we could get the flow of fluid. And how much fluid, the rate that that fluid flows, will depend on the rest of the circuit, what's connected to the other end of the pipe, and so on. And so the flow of the fluid takes on whatever value is determined by the complete circuit. So this is the barrier that we have to overcome. So this is the minimum required delta P to start the fluid current. All right, so that's the kind of fluid version of our diode. Now, the electronic version is going to have very similar characteristics. So in electronics, diodes act as a one-way valve for electric current, or the flow of charge. So let me draw the circuit symbol for the diode. The circuit symbol for the diode looks like this. It's a pretty good little circuit symbol because it looks a bit like an arrow, and the arrow is telling you the direction through which current can pass. If you make this end of the diode positive, not in pressure, but in voltage, more positive than this end, then current will flow from left to right. If, on the other hand, the voltage at the right-hand side is bigger than the voltage at the left-hand side, no current, okay? So this side is called the P side, and this is called the N side. And when we talk about the semiconductor fabrication of diodes, this will correspond to doping semiconductors with positive charge carriers, and this will correspond to doping semiconductors with negative charge carriers. So this is the positive, and this is the negative side. Okay, so if we make the voltage at the negative side, let's call this terminal B. Maybe I'll call this terminal B and I'll call this terminal A. So if the voltage at A is greater than the voltage at B, then I is equal to 0. So that's similar to our one-way valve for water. If, on the other hand, if VB minus VA is greater than some minimum threshold So I'm gonna call that V threshold. Then I is not equal to 0. Okay, so in other words, we require the voltage at P, voltage of the P side to be greater than the voltage of the N side by at least V threshold. And so for the types of diodes that we're going to use, V threshold is around 0.7 volts, 0.6 to 0.7 volts. So we need that voltage difference to be at least 0.7 for non-zero current. Okay, and the idea is pretty similar to what we had for our pipe with the gate, is that to open the gate, we needed to overcome a certain energy barrier. We will see when we analyze semiconductor devices where this energy barrier comes from for the diodes. Okay, so we can plot the so-called IV characteristic. This is going to be similar to the current versus pressure difference we did for the pipe. This time we'll have current, and it's not pressure differences that drive electric current, it's voltage difference. And so this would be like VB minus VA. And it's going to look just like what we had for our water analogy. When the voltage is negative, no current. When it's just a little bit positive, we get no current. And once it passes this V threshold, then the current takes on some non-zero value, and it'll adopt whatever value is dictated by the rest of the stuff in the circuit, like if you had like resistors and so on. And we'll do examples of that today. All right, so let's just see what this will look like for a simple circuit involving a diode. Yeah.
Is it possible for the voltage required to break the threshold to start the flow current is different than the amount of voltage required to maintain the flow current?
No, what we'll do some examples, and we will see that in order to have the current going, we have to pass that threshold, and then we are always going to have that same amount of voltage dropped across the diode whenever it's operating. We'll see how that works right now. Okay, so let's consider cases one at a time. We're gonna introduce this terminology reverse biased. What reverse biasing means is that we're gonna make VB minus VA less than V threshold. And so this is the no current case. Okay, let's draw a simple circuit. So in fact, maybe what I should do, let's do this on a new page. So the circuit that I want to draw is just a battery. Then we'll put in our diode. So this is the P side, this is the N side, and we want the P side positive with respect to the N side. Okay, and then we'll have a resistor. I'm going to call this resistor, I'm just going to call it RL because that's what's in my notes. For this first case, let's make the battery voltage less than V threshold. Okay, so the P side is at whatever the battery voltage is, and the N side is ultimately connected to this ground, and so this is at some lower voltage. Okay, well, in this case, we're going to have a current of 0, because we haven't overcome the minimum voltage required to get the onset of that current. Well, zero current, I could draw an equivalent circuit that does the same thing. So equivalent circuit would look something like this. So we have our battery, and then it's just like our diode is not there. It's like it's been cut out of the circuit, RL. And let's suppose we were to measure the output across this resistor. So it'd be I times RL. So I could put the output over here as well. And so this is our V battery less than V threshold. And this is an open circuit. And this is I equals 0 in our circuit. And if there's no current, then our output is just 0. And that's because I is equal to 0. All right. So what we can do then is from now on, when we see a diode in a circuit and we know the diode is reverse biased, then we could just replace it with an open circuit. It's like we just cut that wire. So a reverse biased diode, a reverse biased diode is equivalent to an open circuit. Okay. So that's the reverse bias case. The other case is called forward biased. So let's do that one. Forward biased diode. The circuit that we're going to do is just the same. It looks the same. We're just going to increase the battery voltage. So here's going to be our resistor, RL, and then we're going to measure the output, V out across there. So now this is V battery is bigger than V threshold. All right. So this is a forward bias diode. And in this case, we're going to have the diode is on, which means that I is not 0. Okay. Let's label these terminals here. This is B and terminal A. And then, so we're going to have a current in here. Our current is going to come around like this. This is I. And so what I want to do is I want to figure out what the output voltage is. So we already know that a forward bias diode requires that VB minus VA is equal to this V threshold. So if we think about that, this tells us that VB minus VA is some positive voltage. So that means the potential here, VB, is higher than the potential at VA. And so it's like the diode is acting like a little battery, where the positive terminal is here, and then we drop some voltage across the diode and end up at A. So in this case, the forward bias diode acts like a small battery, right? So if we had, here's our terminal B, here's our terminal A, this is like, we require the B terminal to be at the higher voltage than the A terminal, B, A. Okay. So what I'm going to do is I'm going to draw an equivalent circuit where I'm going to replace our forward bias diode with this battery. So in that case, the equivalent circuit becomes, well, let's see. We'll have our battery. This was our original battery. VB is greater than V threshold. And then we'll have our diode. I'll leave it out for a second. Let's just draw the rest of the circuit. Here's our resistor. And here's our output, V out. Okay, so instead of the diode, I'm gonna insert this battery. So this battery goes in here and like so. And the value of this battery is V threshold. Like so. So here's positive, negative, positive, negative. And we still have a current I flowing through this circuit. So now what we can do, now this is pretty simple to analyze, right? So we could just do Kirchhoff loop rule. We gain the battery voltage VB, then we lose the V threshold, and then we have minus IR, and now we're back to our starting point. So if we do that, our loop analysis is going to say, well, let's see, VB minus V threshold minus IRL is equal to 0. So that means, therefore, that I, if we solve for I, is VB minus V threshold divided by RL. And so that's what I was saying earlier when we drew the IV characteristic. When the diode is conducting, the actual current you get is determined by, in part, other components in the circuit. So in this case, it's the battery that we had and the resistor. So if we chose different values for the battery or the resistor, we'll get a different current, okay? But the current is on. That's the part that the diode is doing for us. Okay, what about the output voltage? Well, we could say, well, V out is just equal to I times RL. And so it's just the battery voltage minus V threshold. So it cost us something to turn on our one-way valve. It cost us this threshold voltage. But once we surpass that, we can pass some non-zero output to our circuit. Okay, so that's the basics of the diode. Let's see how we can now start to think about these rectifier circuits that are going to be an AC to DC converter. Okay, so rectifier circuit. An AC to DC converter. All right, actually, what we're going to analyze is very much like the circuits that we had just drawn. We're going to have a V in. Instead of a battery, the one change we're going to make is this will be our AC input. And what we're hoping to do is to convert that to a DC output. So the rest of the circuit will start out the same. So here's our RL, here is our output. All right, well, what do we know? If V in is less than V threshold, then what's the current going to be? 0, exactly. That's exactly right. If V in is greater than V threshold, then our current is not equal to 0, and we expect our output to not be 0. Whereas in this case, our output would be 0 for the reverse bias. Okay, so this is reverse biased, and this is forward. Oops, forward biased. In fact, you could probably tell me already, what is the output going to be? I said not equal 0, but what's it going to be exactly? We're going to have our input, and what's this going to become for our forward biased? The little battery, right? So we would drop whatever the V threshold across our diode is. So we would get V in minus V threshold, and then that would tell us what the output would be. So in fact, our V out would just be V in minus V threshold. This is exactly what we wrote down for the case of the battery. All we've done is we've replaced our constant voltage VB with our sinusoidal input. So let's draw that then. So what I'm going to do is I'm going to draw the inputs. So here's time. This is going to be V in, and V in is just a sine wave. So it looks something like this. And then below it, I'm going to draw V out. Out. And here's my time axis. All right. So this here is the amplitude. So maybe our input has an amplitude of V naught or something like that, like so. The other thing I'm going to mark on here is our threshold voltage. And so I'm just going to put it somewhere right here. And so this is going to be the threshold, which is typically about 0.7 volts. So whenever our input is less than the threshold, we have no current. And so those are important points. And so let's mark them like so. So, and then there's actually one more right over here. So this range is, let's say, reverse biased in this region. And it's also reverse biased in this region. And it's also reverse biased here. So our output in this reverse bias place is always going to be 0. No current. All right. And then when we go to the forward biased regimes, forward biased is here, and here, forward biased. All right, well, in that regime, we said the output is just going to be V in minus that constant 0.7 volts. And so what we would expect to see there is something like this, where the height of these little bumps are the maximum, which was V naught from our input voltage, and then we have to subtract off whatever the threshold was. And so you look at that and you say, well, that's okay, but this doesn't really look like a constant voltage. So we're not finished our AC to DC converter, but we have made some progress, right? If I averaged my VN over time, what would I get? It would be a constant. What would that constant be equal to?
0.
0, right? Averaging is like, this is half the time positive, half the time negative. positive, negative, all those cancel out. But this is also going to average to something. It's not going to be zero because this is all the time positive. So we've made a bit of progress. So we've made some progress because, well, the average of Vn is equal to zero. The average of V out is not zero, right? It's some positive value. What we would like to do is we would like to make that output a little more constant. And so here's the trick. So to improve our AC to DC converter, what we're going to do is we're going to put a capacitor in parallel with RL. So let me draw the circuit and then we'll try to understand why that's a good thing. So there's our diode, here's our resistor. This was the circuit we started with. Now what we're going to do is we're going to add the capacitor C, and now we'll take our output across here. And so this is V in. So let's see. The forward biased case doesn't change. We're still going to find that V out is equal to V in minus V threshold. Okay, when we're forward biased, what we're going to end up with is an equivalent circuit that looks like V in. Our diode gets replaced by that little battery, V threshold, V in, and our output is taken over here. So there's our resistor and our capacitor. Here's V out, C on L. There we go. So if we did just tracking change in voltages, V in minus V threshold, and then that just takes us right to the output. So V out is still just V in minus V threshold. But so why is this an advantage? Well, let's think about what's happening here. The resistor and the capacitor they're in parallel. So they have to have the same voltage across them. So what must happen is that this capacitor charges up while the diode is forward biased. So capacitor C charges to V out while the diode is forward biased. Or equivalently, while the current is not equal to zero. Okay, so let's see what happens then when this goes reverse biased. Actually, let me draw the picture. Here's our Vn, and this is time, and here's our sine wave. So this is the exact same. Oh, where'd you go? Trying to draw the same input that we had before. Okay, and then our output is going to be V out. And I'll draw this time over here. And let's see, we can put in our V threshold was right here. V threshold. Okay. So there was these important times, this. Where we had we broke this up into forward bias and reverse bias times. And so while it's forward biased, what we're gonna have is this little peak that's gonna be growing up. And so I'm not gonna fill this in yet. In fact, we drew our output orange, didn't we? Yeah. So I'm not gonna fill in everything yet. I'm just gonna put this little peak here. Because I want to think about now the reverse bias case. Okay, so reverse biased case. All right, so we'll have our V in. It's not going to matter actually, because we're going to have our open circuit, our diodes not passing any current. And so that's like cutting these wires here. And then we have our resistor, RL. Then we have our capacitor, which would be C. And then here's our output, the out. But remember, what's different now is that our capacitor has charged up to V out. So what's going to happen now when we take the diode and the V in out of our circuit? What's going to happen to this capacitor? Discharge through what? Discharges through the resistor RL. So now the capacitor C discharges through RL with a time constant. What's the time constant given by? Tau is equal to what? RC? That's what I heard. There it is. Now, if I want to make something where the output is almost constant, do I want my time constant to be long or do I want it to be short? Yeah, I want to make it long. So C is going to discharge very slowly, or in other words, it's almost going to maintain most of its charge. And so the voltage across it will be about constant. So we're going to choose to make tau much longer than the period of Vn. So the period of Vn is like this time. So let's see, what color do I want to make? Here we go. So this is our period T here. So we want to make the discharge slow. And if we do that, what happens is this starts to lose voltage, but it's losing it fairly slowly. And then what we end up in is we end up back in the forward biased regime where the capacitor is just going to charge back up to V out. And then it'll start discharging again, something like this. And so maybe over time, this is something like what you would see. And in the lab tomorrow, you're going to build exactly these circuits. So you'll first build the simple circuit without the capacitor. And what you should see on your oscilloscope is, and the input is just a sine wave, and the output should be just the positive part of the sine wave. And then you're going to build a circuit with the capacitor in place. We're going to make the time constant long so that you should see this type of shape. Now, this one is more close to a constant value. In fact, what we can do is we can say roughly this is the average of V out. So this is, I don't know, V out average. So with the capacitor in place, V out average increases and looks more like a constant DC voltage. So what would I do if I wanted this to look even more flat? Like less of this kind of, they call this effect here, this effect is the ripple. It's sort of the deviation from being a constant. What would I do if I wanted this to look more constant? Yeah, I could increase tau even more, I get a bigger capacitor, and then it's going to discharge even slower. Another thing I could do is if I can't increase tau, maybe I could change the frequency of my input and make the period shorter so that the time of the discharge gets short. And you can, in the limit of tau being very long, this output would be a constant DC. Yeah. All right, good. Another thing you could do is, I won't draw the circuit, but you're going to build it tomorrow. When you look at this plot, we've kind of wasted a lot of our input, right? We're only using the positive part of our input. We're throwing away all of the negative part. And if we could use the negative part, then we could cut the amount of time that the capacitor discharges in half when it's in place. So there is a version of the rectifier circuit that uses 4 diodes. If you read the lab manual, the circuit is in there and you're going to build that. And when you do, what you're going to find is that without the capacitor in place, we would end up using both the negative and positive parts of the input. And that gives a slightly better version of the AC to DC converter. The other thing that's going to happen in tomorrow's lab, which I think you'll like, is that tomorrow's lab, you're going to complete it and you're going to get your grade before you walk out of the lab. So we're not going to collect your lab notebooks next week. Your grade will be determined entirely by what you do in the lab. So there's 4 parts to tomorrow's labs. Read through the lab manual before you show up. As you complete part 1, you'll raise your hand, show the TA, and if it looks good, you'll get a check mark. Then you'll start working on part 2. When it's done, raise your hand, TA will check it, you'll get a second check mark. If you get 4 check marks for the 4 parts of the lab, you'll get 10 out of 10, okay? If you have anything less than 4 check marks, you're gonna get a 0 out of 10. And the reason is because we are about to make this transition into digital electronics. Digital electronics, you either have on or off, low or high. And so we're going to make your lab mark for tomorrow a low or a high. All right. And so we'll start this transition. What I expect is everyone who shows up to the lab should leave with a 10 out of 10. Okay, that's the goal. So with that, I think we'll end a minute early and we'll see you tomorrow and we'll build some of these rectifiers.
Here's my lab partner. Said we're gonna beat